How we doing? You want to look at the final exam reviews in the workbook, or we could do anything else you'd like? Any questions before we get started with this? Okay, what functional groups are present in Tamiflu? What do we got here?
Amide.
Amide, carboxamide, amide, whatever you want to say. Here?
Ether.
Ether?
Amine.
Amine? Primary, secondary, tertiary?
Primary.
Primary amine?
Ester.
Ester?
Alkene.
Alkene? Cipro? Condensed?
Carboxylic acid.
Carboxylic acid?
Ketone.
Ketone?
Amine.
Tertiary amine, it's really a tertiary aniline. The nitrogen bonded to the benzene ring. Tertiary aniline.
Amine.
Secondary amine. Aromatic ring, that is an alkene. Here, cipamide.
Sulfonamide.
Sulfonamide. Here,
Phenol.
phenol.
Amide.
Amide, and a couple of aromatic rings. Hopefully you know your functional groups by now. Questions about those? Which drug would be most soluble in 2-normal HCl, but not soluble in 2-normal sodium hydroxide? Douglas?
Are you just? I was thinking about this question, and since if I was looking for the one that was most acidic to dissolve in HCl, that's like dissolves like, but I know I'm looking
No.
for I would look for a base to dissolve in the acid. Is that what I'm looking for?
You want to, they're both water. It's not like dissolves like. It's acid-base chemistry.
Yes, sir.
What's going to dissolve in an acid?
A base.
A base.
So the most basic nitrogen.
Usually a base. It depends on what form of the base is. And more specifically, if you can make it an ion with acid. Ions will dissolve in these. Well, what type of compound can you make into an ion with HCl? A base. I don't think you could say all bases are soluble in acid, because sometimes the acid can convert the base into a neutral species, and then the neutral species would actually not be soluble in the acid. Can the acid, what type of compound will HCl convert to an ionic species? Good bases. Which one's a good base?
They all
There's only one up there that's a good base. We define good bases as what? Anions or
are. Neutral nitrogens.
sp3 nitrogens? Which compound has an anion or sp3 nitrogen? None of them have anions.
Tamiflu.
sp3 nitrogen right here. This is a basic amine. It's going to react with HCl. Neither one of these are basic. There's no basic functional group in each. I'm sorry.
What about the?
There's actually
Cipro would be.
There's actually two, because of the way the question is worded, which we're looking for one drug, but it's, okay, I see something now because I see it. We also have a basic nitrogen here. Both of these would be soluble in acid. Does this have a basic nitrogen? No. These two would be soluble in HCl.
Why would the sulfonamide nitrogen not be basic?
Lone pairs in a p orbital.
Okay.
You have p orbitals next door. Same as the amide. I mean, the amide is not basic either. Okay, so there's two that would be soluble in ACL. But which one would not be soluble in sodium hydroxide? What type of compound will give an ion with sodium hydroxide?
Acid.
An acid. So of these two, which one is also acidic?
Cipro and zipamide.
Carboxylic acid.
Wouldn't zipamide also be acidic since it has a phenol?
Yes, but it would not. You're right. Correct. It would not fit this question because it's not soluble in sodium in ACL. Only one of them is the answer to this question. Zipamide does have the phenol. It's somewhat acidic. Phenols are really not called. It's borderline. Usually things aren't called acids until they have pKa below blood pH, which is about 7. A phenol is 10, so it's approaching acidic. It's certainly more acidic than water. It's all just kind of relative. But in terms of, it depends on what base you're using. If you're using sodium hydroxide, then yeah, phenols are acidic because sodium hydroxide will completely be protonated. Yeah. So you actually have two that are acidic and two that are basic. But you only have one that answers this question. There's only one that's both. Okay, can everybody show the result of this reacting with HCl? What would it look like? That reacts with HCl. We identified the basic atom. We got HCl. You can show it ionic or covalent. These electrons do what? Type the H. These move there. And you get the amine coming down. Now it has 3 H's bonded to it. And we make a Cl minus. Cl minus, right? That look good?
No. Plus charge on the end.
Plus charge on the end, standard nitrogen. Of course, we can't just create charge. All that's neutral. This has to be net neutral. But if you just do your acid-base mechanism, it leads to this. I have to first identify the most basic atom. Anions or sp3 nitrogens. sp2 nitrogens would be the next most basic. Nitrogens with the lone pair and p orbital, not typically basic. Certainly much less basic than sp3, sp2. And an sp3 lone, an sp lone pair is typically not basic, like a nitrile. I assume you could show the reaction of this with base. You got a bond here, hydroxide. These electrons take the H. These electrons stay behind. And we get an oxygen with what? Not 2 lone pairs, but 3. And that is a minus. And we also made here water. This side's minus, that side's minus. Of course, you got to have a cation there, like a potassium or something, which would be a spectator.
Just sodium. That's that.
Sodium hydroxide, lithium hydroxide. Which drug above will give a significant N+2 peak in its mass spectrum? Zipamide, right? Chlorine isotope effect. What would be the intensity of this M+2 peak compared to the M+ peak? not as intense. Do you have the intensity, relative intensity of the two?
About 55, 45.
Jacob?
32%.
Hmm?
A third?
I reckon it is a third, yeah. 3 to 1. That's a third if you compare them. Overall, it's 1 out of 4 is 25%. So, yeah, in terms of height, it'll be a third of the other. I mean, it's 3 to 1. You just got to be careful. I mean, in terms of a ratio, this is 75%, 25%, right?
Gotcha.
Huh?
Gotcha.
But in terms of relative difference in the peaks, it's third was a third. If it was bromine, it would be, what's the relative comparison between the M and the M plus 2? Yeah, about 50-50. How many stereoisomers possible for Tamiflu? Jessica Patton?
So far I'm counting 3, so
You're counting 3 what?
stereoisomers.
3 stereoisomers?
Yes, so far I'm still,
The only way it's going to be an odd number is if there's a meso one.
okay.
I don't expect any meso here because there's only one ester in the compound. You're not going to have a mirror plane. You're going to have an ester on the other side. You sure? I thought you were going to say three carbons.
Yeah, that's kind of what I was, yeah, I was counting the power part.
That's not the same as stereoisomer.
Okay.
1, 2, 3, 4. Yeah. So how many stereoisomers possible? 16? Yeah, 2 to the 4 is 16, right? I don't expect any to be meso again because there's not. You got to have the same thing on one side as the other. 16, could you draw 16? Yeah, R would be 1. S would be the enantiomer of R, etc. There's 16 variations. How many DL pairs would there be? 8 DL pairs. Pairs 2. 8 times 2 is 16. How many stereoisomers possible for Cipro? If you look at the actual structure of the drug, it's only one stereoisomer, the 16. I don't know what it is, but it's a very precise stereoisomer. Only 1 out of 16 is actually given as the drug. Cipro, how many possible stereoisomers? Riley, how many possible stereoisomers?
I put
None. Why do you say none? Not any chylocarbons. There's double bonds. Is that stereogenic? Why not? It's in a 6-member ring. If the ring is large, like about 10, 11, or 12, you can have a trans double bond. So you could have a stereogenic alkene and a large alkene, but not in a 6 or smaller. For example, this one over here, was that stereogenic? Apparently not, or unless I just missed it. No, it's not, because it's in a 6 member ring. It can't, that cannot be, this bond cannot go that way and still make a ring. None of these can, none, there's no stereoisomer here. Zipamide, is there any there?
Nope.
No. What type of orbital are the electrons in? This lone pair is in what type of orbital? What's the hybridization?
If the C, the carbon on the left, was connected to a double bond.
We're really looking at the lone pair.
Okay.
Douglas?
Yes. I think it's sp2. It would be sp if there was a carbon. If the left carbon was connected to a double bond, it was just CH3.
Yeah, the lone pairs are sp2. Questions about that? Okay, this guy. Type of orbital is the lone pair in? The orbital. What's the hybridization of the carbon? sp2. Both of these carbons are sp2. But here the lone pair is in an sp2 orbital. Here the lone pair is in a p orbital. What's hybridization of the nitrogen? sp2. What type of orbital is the lone pair in? sp2. Over here, what type of orbital is the lone pair in? sp. You could graph each one of those. Why don't you graph the one on the end? If it's sp, how many hybrids do we have? Two. What's left over? What type of bonds do you see this carbon making?
Triple bond.
Sigma bond to N. What else?
2 pi bond.
Pi bond to N and pi bond to N. and this is all together a triple bond to N. Lone pair has to be where? SP? Don't let the charge there. The charge is meaningless to hybridization. It just happens to be charges on each atom, but it does not affect hybridization.
Can you do the DUS for the first three? Just double check this. It asked the DUS.
I didn't hear.
Can we do the GUS for the first three in number 1A?
Oh, I didn't see
Just double
that.
check.
DUS for each drug. How many DUS?
3.
Four? Does that look right? Uh, uh, 10? Does that look right? Let me tell them again. 1, 4. It looks like 10. Is that right? What'd you get?
I got 9.
It's a 9 also.
9?
4 rings,
We got 4 rings
5 on.
and
That's 10.
6 pi bonds.
Carboxylic acid has a 5 on.
This is condensed over here. Carboxylic acid with a carbonyl. Since it's 10, let's see if we can come up with a number of hydrogens by using that. How many carbons are there? Looks like 17. H, we're going to figure out how many there. There's an F, there's an N3, and there's an O3. Okay, knowing there's 10 DUS, how many H's are here? Don't count. You can count them on the structure, but let's determine them from working the formula. What's saturated for C17?
36.
36. We got 10 degrees of unsaturation. Each one removes 2 H's from the formula. So we got to remove 20 H's, that's 16. But we got, how does oxygen count?
Nowhere.
Doesn't count. How does F count?
Replaces a hydrogen.
Replaces a hydrogen in the structure. I don't think it replaces it in the formula. Yeah, it does. Okay, you got to figure. You got to make sure you're going the right way. Okay. In the end, F and N do opposite things. So one F can cancel one N. You got 2 N's. Really, all you have here is 2 N's. This boils down to 2 nitrogens. So what does nitrogen do?
Adds 1 for each one.
Does it subtract or add?
It adds 2 and going this way.
It adds 2 to the formula? It adds 2 to the formula, yeah. So I think this should be 18. Because if you go the other way, Going the other way, if you see 2 nitrogens, you would subtract 2 to get this number. Depends on which way you're going. Okay, you got to understand it. You can just slip an oxygen into a compound and it doesn't change anything. Okay, we can take this here and we can just slip in an oxygen and same number of H's. But you can't just slip in a nitrogen because it's got to have one more thing bonded to it. And so if you have a nitrogen, it's going to add an H. We've got 2 nitrogens, we add 2 H's. If you're going backwards, though, you're actually subtracting 2 H's. You've got to know which way you're going, and I think it should be 18. For example, if we then say, here we go. Now, if you were looking at this formula, could we get 10 to be DUS? We would say, well, how many H's do we really have? Well, we can ignore that. That counts as one of these. We got N2 left. What do nitrogens do? They add H's. So you say, hey, well, this should be 20. Well, that's where you're wrong. It's already added the H's. And so we actually have to subtract the 2. Because with the nitrogens, that's why it's 18. Without the nitrogens, it'd be 16. You got to know, depending on which way you're going, whether you add or subtract. So here we would actually subtract, and we would see 16. So you can get rid of all of that, and it becomes this. And then you say, okay, saturated would be 36. We're missing 20, 10 DUS. You can also count them, but if you wasn't given a structure and you were only given formula, then you'd have to just work the formula. DUS over here, it's got this sulfur. We're going to get it. We can say whatever we want. If you count these as 1, 2, that's 4, 6, 7, 4 more, 11. Problem is, if you do formula and do it based on formula, you'll probably come up with 9. Because the formula doesn't account for sulfur being able to expand to top 10. So I wouldn't really worry about that. Questions about DUS? Formula for Tamiflu? We should have did that when I did formula for Cipro. What's the formula for Tamiflu? C, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Is that right?
Mm-hmm.
I'll come back and do the H. What do we got? N, 1, 2,
Yep.
O, 4. Oxygen you can ignore. 15 maximum would be 32.
Yep.
How many DUS? What did we say? 4. So that's removing 8 H's, so what's that, 24? We can't just put 24 here because the presence of 2 nitrogens. What do we want to change this to?
26.
26. Well, the presence of 2 nitrogens made us need 2 more H's. Now, if we go backwards, we would say the presence of 2 nitrogens made us need 2 more H's, so this is actually 24. If you get rid of that, you'll call that 24. Then you can say you're missing 8, and it's 4 DUS. Should be 26. Do we need to count them? I don't feel like counting them. Y'all want to count them?
Oh.
Everybody confident you can count those H's? How many right there?
One.
One. Good. All right. Done. Did you know that 2 months ago? How many additional residence structures are possible in each compound? Only counting ones that involve the localization of the charge. About the first one. Two? I should probably reword this. Really, you need to draw them and maybe assess which one's major. I figure you have to draw them to come up with a number of them. How about this guy? How many residence structures could you draw? Two? How about this guy? Four?
I have a question about the second one though. Since the first residence structure will put the positive charge right in the center, and then the next residence would be on the other side, but isn't that just symmetrical with the one that you've got there? So isn't that the same?
It is, but it's considered two different residence structures.
Okay.
They're equal, they're identical, equal contributors. I mean, that's the same thing as just saying here. I mean, the answer is you could show two different residence structures for that. Both are fake. There's only one true structure. Everybody can draw the three additional to this. What does it say? How many additional? Did we say four additional?
Yes.
Yeah, it is four additional. Five total. Everybody can draw the four additional residence structures? Hannah?
I'm a little shaky on it.
Catherine? Joe?
On that one, how would we tell which one's major?
Minus on this oxygen versus this oxygen?
It would be conjugated with the charge.
Probably on this oxygen, because here you have the benzene ring maintained. If you put it over here, the benzene ring wouldn't be really classically maintained. Although that's an argument. Identify charged atoms in A.
Well, before we move on, the second resonance compound, there'd be two that are identical. So both of those are major.
That's tough also, because they're all going to be charged on carbon, and then every carbon, each time it's going to be a secondary. It's hard to also. The only one that's easy to show major is the first one.
Well, if you had the positive charge in the center, then you'd have two pi bonds that aren't conjugated anymore. So would you not count
No,
that
they're
one as
conjugated.
major? Okay.
The whole thing is
Yeah.
The whole thing is conjugated, because they have an empty pure orbital between them.
Okay.
Show the major resonance structure of the first. Major resonance structure. It's not that one. Show the major one. Keep it right there. Questions
What is that major?
as opposed to which one?
As opposed to having them double bond to the oxygen.
Yeah, we could also do this. There are your three resonance structures. Which one do you like best?
Well, that way because you told us.
Well, but you liking this one for some reason. Why do you like this one better?
Well, I couldn't choose between the two.
Okay, well, do they have the same number of bonds? Yeah, so you can't say one has more bonds. So what can you say?
I guess since oxygen is more electronegative,
It is, I agree.
it doesn't want to be positive.
It doesn't want to be positive as much. Nitrogen doesn't mind being positive as much. So the electrons on the nitrogen are going to be more able to move towards the cation. Because the nitrogen is just not as good of a parent. Oxygen holds them tighter. Then you could say, well, but nitrogen is more electronegative than carbon. Why not just put charge on carbon? So why is that better than this one?
It has more bonds.
It has more bonds. And more bonds is one of the leading things. It has more bonds, but you then look at, okay, but then the charge is on the... This nitrogen can donate more. Now, does it donate because it's just a friendlier atom? No. It donates more because it has less protons in the nucleus. Thus, the electrons are not as attracted to the nucleus.
Carbon also doesn't have an octet.
Also, the carbon doesn't have an octet. Here, everything has octets. But since the nitrogen lone pair is not as attracted to the nitrogen nucleus, it's able to just sort of move more towards that plus charge. But we call that electronegativity. The nitrogen is not as electronegative, and it's able, the electrons are... So, now maybe we never looked at that in class specifically between these, but what I'm wondering is, why did you think this one again? Because we saw in class where oxygen did this, and I don't know that we ever did. But that doesn't make it. What was your reasoning though? You wanted the charge to be on oxygen?
I just couldn't choose between the two, but now I understand.
Okay. If this was a minus charge, which would you rather have it on?
The oxygen.
Yeah, oxygen. As long as everything had the same number of bonds, because the number of bonds is usually your first important thing. And with bonds, you're probably also going to answer that octet thing. With more bonds, you're probably going to have everything with octets. So I'd call this major. Where down here, it's harder to say. Down here, it's either minus on oxygen, or you can draw minus on this oxygen. There, it's like, it's going to have the same number of bonds, or both oxygen. Like I said, I think this one here is probably best because you maintain the classical 3 pi bond benzene ring. Charges here. Center nitrogen. Not a standard nitrogen. Likely to be charged. What's the charge? Plus. And out here? Minus. Joe?
I got 2 minus on that one. Yeah, 7.
2 minus on which?
7.
On that one? It owns 1, 2, 3, 4, 5, 6.
I got mine. So you need 7.
Yeah, it's 2 minus. That's because the H ain't supposed to be there. I don't know how it got there. Sometimes when you do chem draw, you put an H on something. No. You're right, it is 2 minus. At that point, you got more than 8 electrons around. I've never, this has been like this for 5 years. I don't know whether nobody's ever caught this. Nobody's ever said anything. Or unless I just edited it, and sometimes when you edit, you throw an H up there. This is supposed to be just that, which is a known compound type thing. You're right, that's 2 minus on the end. This here. Can you show a resonance structure of that? Of the one I redrew. Resonance structure. You could possibly, I don't know if we have to clarify the question. I don't know if there's more than one resonance structure that's possible. Make sure your resonance structure is not terrible in terms of things we've talked about. Can you draw another reasonably good resonance structure there? You gotta be careful about abbreviating these phenols. These are benzene rings, right? These are benzene rings. That being said, don't do any resonance with the benzene rings. That's not going to get you anywhere good. But you drew a double bond here. That's five bonds to carbon. You got to know that the structure of that is okay. But don't do anything with those. If you did, I'd like to see it because it's not going to get you anywhere good. Well, it actually could. It actually could get you somewhere decently, but it's not where I want to go. In any event, that's kind of why I got them drawn as generically, and I didn't want you to do that. But at the same time, you can't start making double bond here because just do resonance structures right through here with these three atoms. Anybody have something?
Where's it at?
Right there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101, 102, 103, 104, 105, 106, 107, 108, 109, 110, 111, 112, 113, 114, 115, 116, 117, 118, 1
Okay. It actually is a good resin structure. Okay. I see now I need to clarify the question. Which one is it? You're missing charges. I think you got some charged items there. What, is that a plus? Why is that no positive? Yeah, you're right. You got 10 electrons around your nitrogen. You got 10 electrons right, so nitrogen can only have 8 electrons around. Hopefully you're doing the two basic things we talked about. How do you stabilize a positive charge? Move electrons towards it. How do you stabilize a negative charge? Move electrons away. Also use your mechanistic arrows to guide you. Hopefully you're not just sitting there and saying, okay, I want to put double bond here and a lone pair here, and boom, I got a structure. No, those two things, then move your electrons. Do we want to move electrons towards this nitrogen? No. Do you want to move electrons away from this one? No. Good place to start with resonances, lone pairs. That's the third thing we said. How about this lone pair? We need to move something towards this. What if we move these in? Can't we just draw another pi bond here? No, then you'd have 5 bonds to nitrogen. Well, maybe we can move this out. And that would give triple bond here, 1 lone pair. What's here now?
Minus.
Lone pair, right? And that's what this arrow means. Now what's a charge? Now that nitrogen neutral. This one's still plus and minus. This is a resonance structure. Now that's sort of looking at the minus and saying, hey, we're going to move electrons away. You could also look at the plus and say, hey, let's move electrons towards it. Well, actually what we did here is we moved electrons away and towards that. But it didn't relieve the charge. There's still charge there. Now, there's no use going to the pi bond, because if we move the pi bond, we would move that towards it. Well, actually, you could. I mean, that would be a resonance structure also. If we move this towards it, what would that give? I'd give it a lone pair, right? And then leave this one like that. Actually, this is not bad in some regards, because what's the charge now between nitrogens?
Neutral.
They're both neutral. Problem is that one doesn't have an octet. And that's usually a bad thing. Although we did relieve charge. See, this is, you're never going to get a good, nice, super nice resonance structure out of this. That's going the A way. The other thing we could do is move these electrons here, going the B way, and that would give you move electrons towards the plus this way. That would give that
Plus on the center nitrogen.
with a positive charge here. It's also a resonance structure where we delocalize the positive. Here we got rid of all charges. Here we delocalize the negative. Again, the problem here is no octet
So the
on
best,
nitrogen. Remember we said you don't want to leave a nitrogen without an octet. So again, we relieve the charge, but that's bad there.
so the best one is the one with the triple bond since everything has octets.
The one on the left is the one I was hoping to get to, but I see that it's not, that's not the only one, because well, if you look at octets, no, atom with no octet, atom with no octet. Everything here does have octets. Problem is, why is this not as good as the original? Give me a reason why it's not as good as the original.
The negative charge.
We put negative on a carbon instead of a nitrogen. Nitrogen more electronegative. In the end, these are your two common resonance structures shown for this thing. Now, I see how I could rephrase the question. I could say, show a resonance structure, alternative resonance structure in which everything still has octets. Then you'd have to get to this, because I don't think there's another one that, okay. All right, let me show you this. This thing without the H, if you heat it, it will form something plus nitrogen gas. Can you show the something? What would it form plus nitrogen gas? You might want to look at one of your resonance structures. And we also made one of these type of general things with a reaction in which we heated it and gave off nitrogen gas. But you should see it on the board here. And what mechanism would you do? By the way, these have the same number of bonds. And thus we just looked at where the charge was. Carbon versus nitrogen. Okay, right here. You see nitrogen here. Nitrogen gas is in, triple bond in. All we got to do is boom. And nitrogen just leaves. How do you make oxygen a better leaving group? Make it positive. What about positive nitrogen? Yeah, if that just leaves, what do you get? You get something plus nitrogen. The something's going to be what?
Carbene.
It's going to be that plus N, triple bond N. But now lone pair is on that end. There's your N2. That's just a lone pair and nothing else there. What's the charge of that? That's neutral. Of course, if a net neutral compound breaks apart, it's going to give net neutral species. That's neutral. This is neutral. But what do you call this?
Carbene.
Carbene. That's a carbene. If you heat that thing, it'll lose nitrogen and give you a carbene. You typically see them drawn like that, but this is a very important resonance structure also. And from this resonance structure, you can more easily see how you can generate your carbene. And it's just ionization. Actually, it's not. It's reverse of ionization because this is ions, and when it leaves, it no longer ions. So it's a tricky case, and when it leaves, it's actually not ionization. It's reverse of ionization. But it's a leaving group. Nitrogen acts as a leaving group to generate carbene. A little bit of heat gets this thing to come off. Okay, so that was the resonance structures of that. We need to remove that H. Which compound has the most negative heat of combustion? Heat of combustion. What is that? It means when you combust it, it gives off the most heat. Most negative. Are we looking for the most stable or the least stable?
Least stable. Least stable.
I think we're looking for the most stable. A heat of combustion is actually a delta H. A heat of hydrogenation is not a delta H. Heat of hydrogenation is an absolute number. That's why I put that delta H there. The more negative the delta H, the more exothermic. And I think Marvin might have been right. I gotta be patient.
Just go with it. Don't think about it anymore.
You said least stable.
Yes. Because I was thinking that least stable, the more stable bonds would be at lower energy. Not least stable bonds would be at higher energy, so to break those less stable bonds would release more energy.
Yeah. We're looking for the,
To me, a negative heat of combustion is release of energy. Positive heat of combustion is endothermic. It's sucking up energy.
yeah. This is most exothermic. Most negative. Which one's going to give off the most energy? The one that contains the most energy. Which one contains the most energy? Most stable or least stable? Yeah. So sorry, you were right. Least stable.
That's number 2 and number 1.
Okay, which one's least stable? Negative heat combustion. Most exothermic. That's got to be right. The more energy it contains. Basically, when you combust these, they're all converted to CO2. They're all isomers, so you get the same amount of CO2. They're all going to the same place. Which one's going to give off the most energy as it goes to that place? The one that sits higher to begin with. That's the least stable. Which one's least stable?
Center.
The T-butyl is the biggest group on each. T-butyl is also bold on each. These are going to be chair conformations. Least stable. The T-butyl, you could draw equatorial on every one. What varies is the methyls. The methyls are next door, here and here. The least stable would be where the methyls are what?
Cis.
Both axial, right? That would be the least stable. The most stable would be where these would be equatorial, and everything would be equatorial. That's the least stable. Which one is this?
Middle one.
All these are cis. Which one is that?
Middle.
Yeah. That sort of makes sense intuitively, just looking at them. All cis, they're all sort of on the same side next to each other. But you got to be careful because that just happens to be the case. If these were not 1, 2, 3, and maybe if it was 1, 3, 5 and all cis, then maybe that's actually good. It really depends on axial equatorial. And don't fall in the trap of thinking all cis is always bad. Because if the methyl was here and cis, would it be axial or equatorial? It'd be equatorial. These are cis. But that would actually be good. They're both equatorial. Okay? So if you wanted to heat your factory by burning one of these, which one would you want to purchase to burn?
Center.
I'd purchase this one, as long as it's cost the same. You're going to get more burn for your buck. It sits at the highest potential energy. When it converts to CO2 into combustion, it's going to give off more energy. Okay, which one over here is going to give off the most energy?
All right.
The one on the right.
Yeah, non-conjugated. Both of these are conjugated. They're going to be more stable. Could you make an argument of which one of these two is most stable?
The middle one is most stable.
Middle one? Why?
It's tri-substituted alkene.
Alkenes are more substituted. Which reactions demonstrate neither regio nor stereospecificity? Somebody have an answer for this?
I said A on this one.
What is cis-2-pentene? 1, 2, 3. Is that cis-2-pentene? HBr. Where are you going to make cation, left or right?
Left.
Either side.
It doesn't matter.
It's going to be non-selective or non-specific. Now, once you make cation, how's the bromine going to add to it?
It's going to add at the cation.
Either way,
Yeah.
you're going to get racemic. Yeah, the answer is A. Basically, look at your reagents. Chlorine and water, is this going to add in a stereospecific way? What are we making here? Halohydrin? The chlorine and the OH are going to be trans. Yeah, we do have a ring. You can just say trans, yeah? Cyclobutene. Is that right? Be trans? But is the OH going to be on top or bottom?
Either way.
Actually, it doesn't matter. It's the same product. So does this demonstrate regio specificity? No, there's no such thing as regio here because it's the same product either way. 1-pentene. Chlorine and sodium bromide. Chloronium ion, Br attacks. Are you going to need chlorine on the left or right?
Chlorine on the right.
Your chlorine on the right, Br on the left. You will not did chlorine on the left and bromine on the right. So it will be regio. Will the chlorine and bromine have a certain orientation to each other? Yeah, they're going to be anti to each other. Now this is going to be able to rotate. One ethyl cyclopropene. Cyclopropene, ooh. That's a strange molecule there. D2 platinum, how does this add?
Right across the side.
In this add, you're going to get a D, and it's going to push this back, plus an enantiomer. Is that regio-specific? Or are you going to get D on the other?
Same thing.
Same thing, right? So that does not exhibit regio. But it does exhibit stereochemistry because you're only going to get the two Ds on the same side. They're not going to be opposite sides. Now if you better define stereo, this will be diastereoselective. But it will not be enantioselective. Because you will get enantiomers. RS here.
Yes.
You got to recognize that that's drawn in a fissure. It's a standard crosshair. It's a fissure. Oxygen is 1, carbon with hydrogen is 2, carbon with all carbons is 3, H is in the back. 1, 2, 3, R. How about this one here? 2 carbons, bromine 1, carbon bromine 2, methyl 3. H in the back. What is this? R? 1, 2, 3. H in the front. What is this?
Yes.
R? No, H in the front.
Yeah, S.
H in the front, S. Is this compound chiral?
Yes.
No, it's compound meso. That plant symmetry right through here. Right? Everybody see the plant symmetry? Well, first off, you got a carbon with 3 things attached. You got a carbon with the same 3 things attached. Are they mirroring each other? Yes, one's R, one's S. Okay. Now, if you want to really see it, you can rotate the bromine up and rotate the bromine down. Bromine up, bromine down. Methyl moves over here, H here. Methyl moves over here, H here. I just rotated some bonds, but now I can easily see the plane symmetry. I knew we were going to see it. Once I determined this R and S, and it's the same thing on top and bottom. Of course, if that was chlorine and that was bromine, it'd still be RS, but it would not be a plane of symmetry because then you'd have a chlorine and a bromine. That'd be the same things attached. If you recognize they're mirroring, then it's going to be meso. Over here, look, H is in the back, that's good. What's 1? Carbon with nitrogen is going to be 1. Carbon with bonds to all carbon is going to be 2. Carbon to just 1 carbon is 3. H in the back, what is this? R?
On that one, you've got a nitrogen in that group there on the right-hand side. So wouldn't that change that to the number 2 priority?
That's a carbon, this is a carbon. That's a benzene ring, right?
Right.
Carbon, carbon. From there we say what is it attached? What's this carbon attached to?
CHH.
A carbon, H, and H. You list the high priority first. What's this carbon attached to? A carbon, and a carbon.
Yeah.
Double bond is like it's attached to 2 carbons.
Carbon and carbon, no winner. Carbon beats H.
You don't get out to that nitrogen. One atom at a time. Okay, identical enantiomers of diastereomers, this guy. One, 2, 3. H is coming forward, so what is this? R? Same connectivity, 1, 2, 3. H is
In the back.
going back, so this is what? S? Those are enantiomers. How about these two?
Enantiomers. Say enantiomers.
Yeah, these are enantiomers. They're both trans. If you just turn this one a little bit, then you see it's mirroring that one. Up here, H is in the back. 1. Carbon with 2 O's is 2, 3, S. 1, 2, 3. H is in the. H is going back.
Yep.
R. Is that right?
Yep.
Enantiomers. Enantiomers.
Got a carbon with an ethyl methyl and an H. Got a carbon with a ethyl methyl and an H. Back carbon has H chlorine methyl, H chlorine methyl. So I have the same connectivity. I better have the same connectivity because all three answers have the same connectivity. These are identical enantiomers and diastereomers. They all have the same connectivity. So I assume they have the same connectivity. The front carbon is this carbon. I can do R and S here real quick. 1, 2, 3. H is in the back. R. Carbon with chlorine is 1, 2, 3. H is in the front. What is this? S. The front carbon is the front carbon S? How do you want to look at that thing?
Yeah, it's us.
How are you looking at it?
I'm turning sideways in my head, so hydrogen's back. And so
You're looking over here with the H going away?
Yeah. So I got a carbon with the chlorine lead first, and then the ethyl, and then the
Yeah, if you look through here, with the H going away, ethyl, this methyl is in front of that carbon going back. So the methyl can be said to be this way compared to the other one. I've got ethyl going straight up. The carbon with the chlorine is going back, that's going back to the hull. So that's going over there to 3 o'clock. The ethyl straight up is 12 o'clock. And then the methyl is at 9 o'clock. So I'm going 3, 12, 9. I'm going counterclockwise. And that is S. Yeah, the front carbon is S. The back carbon.
Also,
Ooh. Here's how I would do it. I would redraw this in a Fisher. This thing is like this, with the ethyl going straight up in the front. I'm going to take it in my mind and turn it like this. And the ethyl's not going to go back. Basically, look at it from like you're laying on the floor looking straight up. And I'm going to draw it like this. Ethyl's going back, but the methyls, the methyl and H, that's the front carbon. Now the back carbon, there's a methyl coming straight down. When I do this, the methyl's going to come forward. I'm actually going to have to rotate the bottom carbon to make it go back. And when I rotate the bottom carbon, the H and the Cl are going to switch. Here it is in a Fisher. This is challenging to get this to see these. This should still be S. 1, 2, 3. Looks like R, but the H is coming forward, so it's S. This is right. 1, 2, 3. Clockwise, the H is coming forward. So it's also S. This is SS, this is RS. What's the relationship? Diastereomers. Yeah. This is challenging to get a good view of it. There may be other ways to just redraw the view. I can see the front carbon. It's hard to look at that back carbon.
The way I did it is I rotated the methyl in the front down so that everything is eclipsed. And then you've got ethyl eclipsing the chlorine. You've got hydrogen eclipsing hydrogen, so they're not the same.
what's not the same? The stereochem, the RNS?
It's hard to explain without drawing it, but rotate the front carbon that way 60 degrees.
Everything eclipsed.
And the hydrogens are on the same side. The chlorine and the ethyl are on the same side.
Uh-huh.
And the two methyls are eclipsing each other. So,
That's
and then rotate that down, and you would see that those two Fisher projections are different.
Or without even taking that last step, once you've rotated like he has, you can see that that same priority, once you do that first rotation, the same priority is in every spot. So they're going to be the same.
Okay, good. Sounds like you've got some good thinking. I think they're diastereomers. Pretty sure they are. Quinine has specific rotation of -170. That's huge. What percent of LeVo form is present in a mixture with a specific rotation of 68? First thing I'm thinking is 68 is what percent of 170?
40%.
Is it 40%? Uh, 40% what? This is plus. So this is not quinine. Plus would be, is that D?
Right.
With quinine being L. What percent L is present?
30.
Okay, don't be so quick to say it's 60% L. No. 40% D. That means the other 60% is what? Racemic. 30% D and 30% L. If you combine the D's, you get what?
70.
70% D, 30% L. What percent of LeVo form? 30%. How many carbons are in quinine? Anybody?
I see 4.
1, 2, 3, 4.
That's it.
Four. Which nitrogen is most basic? sp3. This nitrogen is slightly basic, but not as basic as the sp3. One pair is sp2 over there. Compounds below are decongestants, ephedrine and pseudoephedrine. What's the relationship? Anybody?
Diastereomers.
Diastereomers. The HCl salt of ephedrine has specific rotation -34. What would you predict for the specific rotation of the HCl salt of pseudoephedrine? I would predict that I don't have a clue. You cannot know. Both ephedrine and pseudoephedrine can be dehydrated to an alkene, which upon hydrogenation produces methamphetamine. How many stereoisomers exist for the alkene?
Two.
Where are you going to dehydrate? Removing H2O? Okay. OH and a beta hydrogen, H2O. Double bond here, yeah?
Yeah.
Double bond here, it's the same thing. How many stereoisomers possible for the alkene? Two, E and Z, right? How many stereoisomers are possible for meth? Which can be hydrogenated. If you hydrogenate the double bond, what's the structure of methamphetamine?
Same thing as that, except replace the OH with the H.
Yeah, because you first eliminate, make the double bond, that gone. Then when you hydrogenate, you add an H there and an H there. You're putting the beta hydrogen back, and you're adding one more here. Methamphetamine is this. How many stereoisomers are possible? One carbon, 2, R and S. That's a methyl there. What if you take this methyl off, replace it with an H, what do you have? Not methamphetamine, but
Amphetamine.
amphetamine, yes. Usually in organic 2, I show you other ways to synthesize methamphetamine. I also get my good buddy Brian Cranston to come in and talk about some of the methods that they used on the show. He's a fascinating dude. Which one of these would you like to do?
First one.
First one? Sodium and ammonia, what's that going to do to this alkyne?
Break the triple bonds.
This is not sodamide. This is not sodium ion, the NH2 minus ion. This is sodium and ammonia. What's that going to do to an alkyne?
Pull off the hydrogen.
No, this is not NaNH2. That's Na plus and H2 minus. This is sodium metal and ammonium gas. It's that reaction where you put the sodium in the ammonia, liquid ammonia, and you get dissolving metal electrons, or dissolving electrons, solvate electrons. Okay? You're going to get the trans-alkene. Of course, you're not going to get trans here because there's no cis and trans possible. You get the same product if you used hydrogen and Lindlar's catalyst. You get the same product. If your alkene's not stereogenic, both methods get the same product.
I'm sorry, what is the sodium and ammonia doing? Is that the one where it's
Radical reaction, dissolving metal reduction. That was one of the last reactions we looked at for alkynes. That was our first look at a radical reaction. That was also the answer to one of the multiple choice on test 2, where the alkene was trans. And sodium and ammonia is what gave that product. You got test tube with you?
No.
I can test tube like on the second page near the bottom, I think. Okay, if you get this alkene, what is, this is really oxymercuration followed by reduction. This is really a combined two-step process that we know well. What does this do to an alkene? Hydration by Markovnikov, and we're going to put OH here. No. That's just conversion to the alkene and then a Markovnikov hydration using oxymercuration. Isopropyl acetylene. That's acetylene with an isopropyl. H2 Lindlar's catalyst. Well, that's the same thing as up above. That's going to convert this to the cis alkene. But this alkene doesn't have any stereochemistry, right? So it's just now we're doing a very analogous, what are we doing here? Antimicrobial. So we're going to hydrate by putting an OH on the end, right? It looks like we're doing alkyne chemistry. 1 decine. What is decine? It's a 10 carbon. There's 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8. Is that 1 decine? Oh, NaNH2. Now we're doing, what does that do? Removes the terminal H. Now we throw in, well, that's a long old primary halide.
Yeah.
Yep. And so now bonded here is going to be how many carbons?
14.
We made that bond, there's what?
14.
1, and then there's 12. We can group those together with a CH3 on the end. That's a long internal alkyne now. And now what does Lindlar's catalyst H2 give?
Alkene.
It's going to give this, but this is going to be
Trans.
cis.
Yeah.
Cis. So I'm going to draw it. I'm going to have to keep the right number of carbons. There should be, make sure you right number of carbons, because it's going to be a cis alkene. That's just a big old alkene with lots of carbons. This is actually a sort of a known compound that we just made here. This compound is present in like fruit flies and just regular house flies. I think it's used as sort of a pheromone. It has some type of hormone properties fly uses. It's been isolated. Just a long old hydrocarbon with 1 alkene that's cis. One dichlorobutane. Excess of NaNH2. Probably chose IR peak of 2180. What are we doing here? Do that twice. Double E2 elimination, what do we get?
Con.
The double, and what's the peak at 2180?
Carbon triple bond.
Carbon-carbon triple bond. Looks like these are all alkyne reactors. Except the last one. Now if we do aqueous acids, mercury sulfate, What are we doing to the alkyne? You did it in lab. You didn't use mercury though. Hydration of the alkyne. What you gonna get? OH on left or right? OH over here. Boom, boom. OH over here. So there we go. We hydrated it once. We're going to hydrate again, or is this thing going to do something? It's going to do something. It's going to tautomerize. And the peak at 1710 is your carbonyl. Ah, the old diene reaction with HBr.
Not stable.
How's that look? Questions about that? If this double bond reacts, you're going to make cation, you make secondary, resonance would be tertiary. If this double bond reacts, you're going to make tertiary, and with resonance would be primary, so which is best? That. This double bond is best. So we're going to react here and get cation here. If we did resonance, we put cation there to give secondary, tertiary. But is bromine going to add here and give this, or do we want to do resonance and have bromine here? Well, that would be a tri-substituted. Tri-substituted. Double bond there is I'm missing the methyl. Tetrasubstituted. Tetrasubstituted is best, so it's actually a 1,2 addition product, even though we're doing heat. Because the 1,2 product is actually the most stable.
Since the first step of this is going to form a carbocation, is it safe to say off the bat that it's going to do the one that's, it's not going to do the most substituted alkene because that one's too stable? Or do you need to go through all the steps?
I think you need to go through all the steps.
I saw that as a maximally, like the maximum possible stability on alkene. I couldn't imagine it.
Well, if there were two methyls here, based on what you just said, you'd still do the tetrasubstituted. You would still avoid that?
Yeah.
Actually, there are two methyls here. This would be the alkene that would react.
Yeah.
Because you'd make tertiary, tertiary. Where if you reacted here, you would get secondary, tertiary. So what that your statement doesn't hold up there. Diels-Alder. You recognize this as the Diels-Alder? I mean, these are just pi bonds. There's no acid catalyst or anything. It's just pi bonds reacting. It's Diels-Alder. It's the only thing we look at for just pi bonds reacting. You got a diene here. You got a here. You're not going to react benzene in this class. One equivalent of each. And we're going to get, can you draw that product? make that bond and that bond. 1, 2, 3, 4.
Double bond between the 2 and 3 carbons.
Yes. One, 2, 3, 4. If we zip it together, boom, boom, and right there is your double bond between 2 and 3. These groups over here will be cis. There's a cis here. You can go on to get estrogen type hormones. If you look at those hormones, they have the 4 rings like this. Only one equivalent. If you use 2 equivalents of this, you can maybe get a Diels-Alder on the other side. Maybe build your 4 plus 2 over here. Which reaction would be best to make the compound in the box? In both cases, we're doing an E2 elimination. Which would you rather use, methoxide or T-butyl oxide, terbutoxide? You'd rather use that. There's only one alkene possible. Why not use this over here? Because this is more likely to do SN2. Sterically hindered base, less likely to do SN2. If you only want elimination, now there's only one alkene possible. It's not like we're having to worry about getting the Hoffman versus Seitzek. How about down below? We're using the same base. Would you rather make this compound starting with this bromide or this bromide? Which starting material would you rather use? Mackenzie, which reaction would you rather do? What?
Not sure.
Jacob? Veronica, you got which one? Fabian?
Second on the right.
Why the one on the right?
You know, substitute alkene. Not sure what.
What do you mean more substitute alkene? Both theoretically give this product.
The one on the left also gives a product with the top part, an alkene.
The methyl reaction.
So that's a
One on the left because of the
You can put double bond here or there. Down here is the same as there. But over here, you could put double bond there, which we want, or there, which we don't want.
right, that's what I'm saying.
So they both have 2 options.
The one on the left has a bad option, so the one on the right is a higher.
What do you mean? Why is putting double bond here not bad? Because that's not this. Here the double bond is to the carbon with the methyl. Why is that not bad?
I see what you're saying.
No, that's bad too. We don't want that, so it's bad. Riley, what you got?
I would do the one on the left
On the left? What?
because the beta
There's two here. One of them will be, yeah. When you got two, you don't have to worry about that. Now, I'm not showing any stereochemistry here. So, I mean, you could have a scenario where this H would not be. But I'm not really showing stereochemistry, so you can't really address it. It depends. It either is going to be or not, but it's, I mean, if these were both, if these were trans, then that would not be a good root.
But you know that you'd have to know how that was made, right?
Yeah. I think here's when I put this together. Over here, you could get substitution. Is this going to have any competing substitution? No, because you don't do substitution on tertiary halide. So that's what I was going at here, especially with the undefined stereochemistry. That means you can't address it. But I do see that. I could modify this and say, hey, let's make this like that, and this like this, where this is not chiral, so there's nothing to show there. If it was like that, then you would say, boom, clearly it's got to be this, because this one is not going to eliminate. Is that right? Because the H here is cis to the bromine. But this is what I was thinking. Actually, with both of these, that's what I was thinking. You gotta be careful when you want to do elimination. You got, you know, substitution could compete with it. How would you do these? Let's do the very bottom one. How would you eliminate this to give the alkene? That would be what type of product? Hoffman?
Yeah.
What would you want to use down here?
Tert-butyl oxide.
Yeah. Maybe stereochlorhinder, that's a common base. We need Hoffman, right? How do you get more Hoffman? Various stereochlorhinder bases. What's going on with here? One step. What do you want to react this with to get
Methoxide.
maybe NOCH3, which is essentially OCH3 anion, right? Okay, you can just use that. We know how to make this. We would take methanol, right? Treat it with sodium. We give that. Or you can just use it as a reagent. I mean, you can just buy them. That would give that, right? Backside attack, so it comes in from the back. Good old SN2. How would we make this alcohol up here? Either one or two steps. There's two different ways that I can think of. One step, how would you do it? What type of mechanism we want to do? Substitution or elimination? Substitution. OH replaces bromine, but it's not on the same carbon. Somehow it migrated or rearranged. So do you want to do SN2 or SN1? SN1. Okay, so what reagent? You would supply the OH and do an SN1. No, hydroxide would do SN2. Water. Water and heat. Might we throw anything else in here with it? We want this to ionize, and we want the H to hydride shift over and make cation here,
Silver nitrate.
and then have water attack. Yeah, maybe throw in some silver nitrate, up and ionize. Basically, you want SN1 with rearrangement. SN2 would not rearrange. SN2 would be like we did down here. I mean, you could use hydroxide. Hydroxide can be a nucleophile for SN2, but you would have an OH here. And since it was SN2, it would be inverted. I would say this would be racemic, but it's not chiral. So that's a one-stepper. How would you do this in two steps? Two steps. Two totally separate steps. That is, you convert it to something, and then convert that to the final product. This takes a little ingenuity here. Maybe one of these steps is a test 2 reaction, and the other one's a test 3 reaction. Let's go over here. How do you make alcohols? How have you made alcohols in this class? Well, we just made it by an SN1 substitution. How do we make alcohols during test 2?
Hydration
Hydration of
of an alkene.
alkene. What alkene would you want to hydrate? If you had that, which is not stereogenic, could you convert it to this? What reagent would you use? Would you make cation on left or right?
On the left.
Left, it'd be doubly resin stabilized. You could just use H3O plus and do an acid hydration, or you can use oxymercuration. Okay? Can you convert this to that alkene? What reagent would you use? Now we've already said that KOT would give this alkene. How would you make that alkene? Maybe KOH?
Yeah.
Gotta be careful though. Hope for, what are we hoping for? E2 and not SN2? See, here you just have to hope. Because it's not sterically hindered, it could do SN2. But if it does E2, it's probably going to give Zaitsev, which that's the Zaitsev product. Is there another way to do this? What about E1? Well, E1 and E and SN1 compete. I mean, we could treat this with like water and silver nitrate, hopefully it eliminated. But instead it may hydrate. Both of these are tough. Maybe this would actually give this product, and to get the Hoffman you have to use an even more sterically hindered base to get the Hoffman. But this would be a two-stepper. If we can convert it to the alkene and then hydrate it, that'd be a two-stepper. So we're thinking about synthesis multi-steps. Hopefully when you see that, it makes sense. What reaction would give the top product? We're apparently removing an H. What reagent would you use? yikes, the H and the Br are cis. Would you want to do an E2?
No.
Now, one thing we may not have clarified here is, yes, the D bond is stronger to break, but the anti is better than the syn. It would still break the D. And actually, this down here is where you do your E2. I'd use a base. Either way, you get the same product, such as KOT. How do you want to do the top? E2 or some other elimination? It's going to have to be E1. E1, I would do like ethanol and heat or something. Ionize off. Make cation. From there, which one of these are you going to take to put in the double bond?
The H.
Yeah, the weaker one. Now this is a fast step. But still, you're going to do the better one in the fast step. Where if you do E2, you're breaking the beta hydrogen in the rate determining step. But also anticoplanar is actually, it's kind of apples and oranges here. You may wonder, well, is it more important to remain anticoplanar, or is it more important to break the weaker bond? It's more important to be anticoplanar. If you say you're going to break the weaker bond, then you would get H here in both cases, and so then how would you do it? Okay, I've got time to do one mechanism. Which one would you like to do?
One with the TEA,
Anybody have a suggestion?
C,
Which one?
letter C. It's not showing right now.
Okay, C is a little bit unique, but it's pretty straightforward in terms of just thinking. One bromobutane, reacted with that, and triethylamine. This is a neat way to make aldehydes. What could you do over here with these reagents? We know we got a leaving group. Okay, that's the only chemistry you can do here. It's leaving group chemistry here. We have a nucleophile.
Yeah.
O minus. Now triethylamine is potentially a nucleophile, or you could do elimination. But ultimately, we got to get an oxygen bonded to the N carbon. And ultimately, we got to get two bonds. But right here, we got an O minus, boom. We can kick this off. What does that do? It gives that bond right there, right? Plus Br minus. My SN2. There's nothing really new there. Just an odd-looking starting reagent. That's net neutral. Okay. Now we need to make a double bond between the C and the O. There's two H's here. There's only one on the N carbon there. Two. We got to remove an H and the thing from the oxygen. The increment on the oxygen is positively charged. How can we do this? These electrons take an H, these electrons move in, and these electrons kick off. What does that look like? That gives that plus the leaving group. Nitrogen gets a lone pair. Now the trifluorine has an H. Have a positive and a minus, a neutral pyridine and a neutral aldehyde. E2. It's just an E2, but instead of making a carbon-carbon double bond, we made a CO double bond. Yes, you can do that. It doesn't have to be carbon-carbon double bonds. Does that look like an E2? Concerted elimination, you take the beta hydrogen, electrons move in, kick off the leaving group from the atom. Positive nitrogen, is that going to be a decent leaving group? Now goes to a positive oxygen. A little bit unique, but do you see the chemistry is very classical, very standard? Question?
Isn't the oxygen
How's it look, Joe?
I was just wondering, have you seen leaving groups of oxygen before?
We've seen leaving groups in carbon.
Yeah, but I thought it would be carbon.
Yeah, you would not do it on a trigonoplanar carbon.
I just don't know.
I never said it had to be carbon. I just said it had to be tetrahedral. That doesn't imply that it can't be. I was really getting at it can't be a trigonoplanar carbon. Yeah.
So a tetrahedral something, whatever.
Well, I mean, usually we focus on things, but I mean, when you get outside the doors here, there other things can happen, but it's very analogous. It's just like, how do you make oxygen a better leaving group? You always say protonated. And I'm like, well, be careful. There's more ways than protonating. Really what you're doing is making it positive. There's other ways to make an oxygen positive other than protonating. I'll tell you this as the last thing. We said you never do SN2 on a tertiary halide. For example, you do SN2 on this. Would you?
Probably not.
You should not do it. Okay? Well, guess what? Make that silicon, which is right below carbon in the periodic table, and it has the same bonding. Silicon makes 4 bonds. Can't do SN2.
we're not gonna have that on the test, right?
No, this won't be on the test. Okay. The silicon's bigger. Because it's bigger,
More space.
there's just more room to get to it. Silicon also has d orbitals, and those d orbitals may contribute. But some of the things we talked about are precise to carbon. Some things we talked about are not necessarily just precise to carbon. Here we're making a CO double bond instead of just an alkene. Okay. In the end, how else would you do this mechanism? And could you use basic principles that we've been doing here? Trusting that it's not going to be something that you've just never really seen. To a degree. I mean, you've seen nucleophiles displace bromines. this point, you just like, how can I get a double bond in here? Obviously, the nitrogen has to leave the oxygen. It's no longer there. I mean, do you want it to just leave and leave the oxygen with no octet? It doesn't sound like something you should do. So your other option, well, maybe I'll do a concerted elimination, because I do have to remove an H, because there's only one here now. Where there's two on the end. So I got to remove an H, I got to get rid of a leaving group, because it does leave. What are ways that you've done that? So use your ways. And yes, it's an option. Okay. I've got to go, guys. Hope this was useful. Have a good weekend. See you.
Do you have any
Monday.
labs graded that we can get back in your office or anything?
I don't.